Hi, I'm Dave Brown for Teletrain, and today we're going to cover the first part of Lesson 8 of Parker Hannifin's Industrial Pneumatic Technology, which is entitled Directional Control Valves. All of the units you see here are directional control valves, and their primary purpose is to control the direction of air flow in a pneumatic circuit. In certain applications, however, directional control valves may be used to control other functions in an operation. For example, selecting the higher or lower of two pressures. Most directional control valves work on the same principle. That is, they consist of a valve body, here, with ports, like these, here and here. As you can see, the ports are connected to these internal flow passages, and by pushing this movable part back and forth, we can change or control the direction of air flow. One method used to classify directional control valves is by the number of flow paths that are set up in the various operating positions. So you will hear them referred to as two-way, three-way, and even four-way valves. Here is a two-way valve. It has two ports, here and here. The spool shaft extends through the end of the valve body, here. As you see, when the spool is in this position, we have a passage here and here, which allows airflow through the valve. It has a symbol which looks like this, and it indicates that there is airflow through the valve. Okay, that's one function of a two-way valve. But what happens if we were to move the spool? Well, if we push the spool over into this position, we close off this opening here, and no flow is allowed. Here is the symbol used to indicate that the flow path through the valve is closed. The complete symbol for a two-way valve is the combination of the two. This indicates an open flow path, or passing condition, and this a closed flow path, or non-passing condition. Most applications for two-way directional control valves use a spring to bias the spool in one direction or the other. This type of valve is called a spring offset, or spring return. In this case, the spring is holding the spool so the passageway through the valve is open. If we wanted to stop airflow through it, we'd have to exert a force on the spool shaft. Right here we should explain two terms you will probably be hearing. They are normally open and normally closed. What the normal flow condition means is that when there is no external force on the spool, the spring will bias or offset it to one end of the valve or the other, depending upon where the spring is placed. So the position to which the spool moves when there is no external force on it is called its normal position. With the spring as it's located here, this valve would be normally open. Here is how we would represent it using a symbol. Note that the spring has been placed on the side which identifies its function in the normal position. So here we would have a two-way, spring offset, normally open, directional control valve. If we put this valve in a circuit, then we always position it so the lines are connected to the side that indicates its normal position, like this. The valve you see here is another two-position valve. It is a three-way directional control valve, and it is normally used to pressurize and exhaust one leg of a circuit, such as a spring return cylinder. This cutaway shows the parts better. Here are the three ports, port A, port B, and port C. Port A is normally connected to an actuator, port B to the air supply, and port C is left open as an exhaust. When the spool is in this position, there is a passage for air to flow from the supply through the valve to the actuator here at port A. The exhaust port is blocked, as you can see here. If we move the spool into the other extreme position here, The supply is blocked off here, and port A is connected through this passage so the air can exhaust from the cylinder. Here is the symbol used to represent the three-way control valve. In this position, the actuator can be pressurized, and in this position, air is being exhausted from the cylinder. One of the most common directional control valves used in industry is the four-way valve. It is frequently used to obtain reversible motion either in a cylinder or a pneumatic motor. This is a four-way valve here. In this position, port A is connected to the supply or pressure side, and port B is connected to the exhaust. And if we move the spool to this position, port B is now connected to the supply, while port A is connected to the exhaust. Let's see how this can be used to control the direction of an actuator in a simple pneumatic circuit. In this circuit, the four-way valve is connected up to control the direction of a cylinder. This is the line from our pressurized supply. In the position shown, there is a passage for air to flow from the supply through the valve into the cap end of the cylinder. The rod end is connected to the valve and air exhaust through here. Under these conditions, the rod will extend. When we move the valve into the other position, the supply pressure is connected to the rod end of the cylinder. And we've created a passage for air to exhaust from the cap end through the valve to the exhaust port. So you can see by using the four-way valve, we can easily and quickly control the direction of a pneumatic cylinder. Four-way valves are also available with 5 ports and provide the same basic control of flow paths as the 4-ported models. Sometimes it's necessary to hold the spool of a 2-position valve in the desired shifted position, and that's the purpose of these notches you see here. They're called detents. In this case, the detents are notches that have been machined into the spool shaft, although some manufacturers use grooves. Their purpose is to serve as a receptacle for a spring-loaded movable part like the small ball. When the ball drops into the notch, the spool is held in position. When the spool is shifted, the ball is forced out of one notch and into the other. So in use, the actuator force only acts to shift the spool. These detents help hold the spool in the desired position. We should point out that detents may not always be adequate to hold the spool in position if there is a large impact, heavy vibration, or sudden surge of air. In these cases, other design techniques will have to be used. All of the valves we've examined so far are 2-position units. That is, they set up flow paths when the spool is in one of 2 extreme positions. The valve that you see being used here provides some additional features. It's a 3-position 4-way valve. In fact, we'll be looking at a family of 3-position valves shortly. But first, you should understand why 3-position valves are so useful. We've already shown that the 2 extreme positions of a 4-way directional valve are related to the actuator's direction and could be referred to as the power positions of the valve. The center position of a 3-position directional valve is used to satisfy a system requirement. For this reason, the center position is called the neutral condition. Here are the symbols used to indicate how valve ports can be connected for center or neutral valve conditions. Note that the symbols show a 5-ported valve. There are 3 ports on one side and 2 on the other side. This symbol indicates that in the neutral condition, both cylinder ports will be open to the exhaust, and the pressure port here will be blocked. This type of center condition is called exhaust center. This type of valve connection is called pressure center. In this case, when the valve is centered, both cylinder ports will be connected to the supply center. And finally, we have this case, where all valve ports are blocked when it is in the center position. What do you think this hookup is called? Blocked center? How'd you ever guess? Now, suppose we had an application where we wanted the rod to be free to move when the valve was in the center position. What valve configuration would you select to do this job? Well, the right circuit would be the exhaust center hookup, and here it is. When the valve is in this position, pressure is supplied to the cap end through here, and the rod end here is connected to the exhaust. In this valve position, the cylinder will extend. If we shift the valve way over to the other extreme, we've connected the air supply to the rod end, and we're exhausting here from the cap end, so the cylinder will retract. When the valve is centered, you can see that the supply is blocked by the valve here, and that both the rod end and the cap end are free to exhaust. The big deal is this. See how the rod is free to move in either direction when the valve is centered? This is a particularly useful feature for certain circuit applications. Now, if what the system requires is a rod that can be stopped and held in position, we would use a valve with a blocked center condition. As you can see from the diagram, with the valve in its neutral state, both ports of the cylinder are blocked. So once pressures on each end balance out, the piston will stop and remain where it is stopped. In the pressure center condition, pressure is maintained on both ends of the cylinder when the valve is in its neutral position. Since the piston area on the rod end is smaller than the area on the cap end, the piston will extend, but comparatively slowly because of the back pressure on the rod end. This pressure-centered valve can be used to reduce cylinder lunge or jump that results from startup with no back pressure. Okay, then, you've seen that directional control valves are classified according to the flow paths that are possible, and that they are available in 2-position or 3-position models. Now let's talk about something that is common to all directional control valves: the external force that is required to shift the spool. Valve actuation may be accomplished in a number of different ways. Here are their symbols: manually, mechanically, hydraulically, pneumatically, and electrically. Manual actuation is simply where we use human energy to push a button, shift a lever, or step on a foot pedal. Manual actuation is used on systems which require an operator to direct the movement or sequence of operation. Mechanical actuation is usually accomplished with a cam. A cam is simply a valve with a roller or ball mounted on the end of the spool extension. The roller is in contact with some part of a machine, frequently a cam which is mounted on a cylinder rod. Mechanical actuation is used when the valve spool must be shifted when the machine being controlled reaches a certain position. Often, an electrical solenoid is used to shift the valve. A solenoid can be constructed by winding a wire into a coil. Then, into the hole in the coil, we insert a piece of iron, or plunger as it is called. When we pass a current through the coil, a force is exerted on the plunger like this. Quite often, the coil for a directional valve actuator is covered with insulation or encapsulated. When a solenoid is used to operate a valve, the electrical current flowing through the coil causes the plunger here to move this push pin. This force shoves the spool over, as you see here. Solenoid actuators may be used on only one end of a spool and use a spring return, or they can have double actuators which shift the spool first in one direction and then the other. Here is what the symbol would look like if we had a four-way, spring offset, solenoid activated, directional control valve. When either air or hydraulic pressure is used for actuation, it is called pilot operation. In pilot operation, either air or hydraulic pressure is used directly against the end of the spool, or a separate pilot piston may be used to do the job. In the valve shown here, pilot pressure is applied directly to the end of the spool. When the force of the pilot pressure on the piston exceeds the force of the spring, the spool shifts, and the supply would be connected to the outlet. Pilot actuated valves may be internally or externally piloted. If the pilot pressure comes from a source within the valve, it is said to be internally piloted. If the pilot air comes from a separate source, it is said to be externally piloted. As you might suspect, the larger the valve, the greater will be the force necessary to shift the spool. So while the solenoid you see here couldn't develop enough force to shift the spool of this valve, we can shift the spool by using the pilot operation like we just discussed. What we do is piggyback control valves, and we use a solenoid to shift a smaller control valve and use its output as pilot pressure to shift the larger one. Here is a configuration that would do the job for us. We've got electrical solenoids to activate these smaller control valves here, and their output is used as supply pressure for this larger air-piloted valve. If we activate this solenoid, this valve will shift, and pressure will be sent down this pilot line and cause the main valve to shift. Then, if we activate the other small valve, the main valve will shift back the other way. The complete name for this type of setup would be a four-way, two-position, solenoid-controlled, pilot-operated, directional control valve. For convenience, these valves are often sub-base mounted, which means the directional valves are fastened to a base to which the system piping and power is connected. As you can see, sub-base mounted valves make servicing a whole lot easier because the piping doesn't have to be disturbed in order to install or remove the valve. This concludes part one of our discussion of directional control valves. We've covered the information on pages 81 through 86 and 92 through 94 of your text. In the next program, Lesson 8, Part 2, we'll cover the remainder of Chapter 8. I'm Dave Brown for Teletrain.